Okay, any questions? So the last thing we did was the high school division with the power series. And like I said, I did a real kind of fast and loose proof on that where I sort of divided it out. And I hope you all got the idea. Really, all you need is the constant term per unit, and that allows you to create the next term. And since it's a power series, you never have to stop. So that actually gives you the inverse. And of course, this also is shapes to what you would actually do if you would have been the formal proof. And what you do is you assume that you start by making the inverse of some power series, the inverse of the constant term, which is a necessary condition. Then assume that you built the first n terms of the inverse, and you can inductively build the n plus one term of the inverse. So it's not super difficult. Of course, note behavior of units for Rx and R power x are very different. And as I pointed out last time, the size of the units of Rx is the same as the size of the units of R, so in particular it can be finite. But for R power x, in any ring that has an identity, R power x has an uncountable unit group, which is, that's a big contrast. Here is something that follows from this. So the units behaving this way, power series, I mean, in a certain sense, you could get into a big philosophical argument with somebody about whether it's easier to be units, polynomials, or power series. And the argument that polynomials are easier is the units are the same as in the coefficient ring, right? The argument for power series is all you need is a unit constant term and you're good to go. Here's something, however, that definitely I think is better for power series. If A in R is an irreducible element and f of x and R power x is such that f of 0 equals a, then f of x is irreducible in R power x. Right. And this actually takes advantage of this units proof. Sometimes I'll use that notion to denote the irreducible elements of an integral domain. And keep in mind that for some integral domains, this could be the unit set. Suppose you have f of 0 is a is irreducible, and suppose f of x is g of x h. Okay, I claim that one of these two has to be a unit. Note that a, which is f of 0, is g of 0, h of 0. So what you have is A factors into two elements in R. So G of 0 is in R without loss of generality. Because A is irreducible, so any factorization 1 to 2 must be a unit. Therefore, G of x is in U R power x. So there you go. Right. So if you spy a power series that has an irreducible constant term, it also is irreducible. And of course, this is wildly untrue for polynomials. There is a polynomial, for example, that has let's say that we're sitting in the ring ZX. Its constant term is the irreducible 2. In fact, it's prime even. But there you go. It factors non-trivially into two polynomials. And notice, of course, the catch is that second polynomial factorization as a power series is a unit. All right. Okay. Any questions on that? Okay. So, one of the big questions in my research is how, or one facet of it anyway, is how factorization behaves in extension rings, localization, polynomial, power series, etc. And we're going to look at that. We're also going to look at another important kind of ring extension called an interval extension in a bit. But let me type some loose ends of these power series proposition. Let's let one and an ideal then this thing, I define this analogously to the way I did it for polynomials. This is a set of power series where all the coefficients are in I. This one needs less explanation, I think, because again, this is the ideal in R power X. It's the smallest ideal that contains the set I and the element X. Our ideals in R power X, just as before, and the exact analog is the same. Number one, if you have R power X mod I power X, this is isomorphic to R mod I power X. So it's still a power series ring, coefficients now in R mod I. And two, R power X modulo the ideal generated by I and X is isomorphic to R mod I. And so IX, I power X, or respectively, I comma X is prime in R power X if and only if I is prime in R. And there's also something to be said for maximal ideals as well. Okay, so let me kind of wave my hands at this at least. The proofs of these, again, are almost the same as what they were for polynomials. Again, I'll let you all show. I mean, of course, this is an ideal just by definition, because it's the smallest ideal containing I and X. And this, it's pretty easy to see that if you add two power series, all of these coefficients are in I, you still get something all of these coefficients I. And if you multiply that power series by something in R power X, it's a vacuum cleaner out the wazoo, right? It's sucking all the coefficients in, right? So these are ideal. So let me sketch out the proof. I didn't even sketch. To verify 1 and 2, consider 1 phi from R power X to R mod I power X given by phi of down here. Phi of Ri Xi equals Ri plus I Xi. Just consider that function and is an epimorphism of rings with kernel I power X. And so the first isomorphism there will be straight up. And you do something similar to it. The other one, you just modify that homomorphism a little bit. The other one, the way you do this one is Rnxn equals Rn psi. And here, this is also on an epimorphism of rings with, in this case, kernel is my bad. Of course, this should be R0 SI. You guys on power series anymore. So what this does is it reads the constant term and just takes its cosine represented by I. This last remark here, I power X, respectively Ix prime and Rx, if and only if I is prime and R. Well, of course, if I is prime and R, this is a domain, which means this quotient is a domain, which means Ix is prime. And if this, right, and if I is prime and R, then this is domain power series X, which is a domain in the same, which means that I power X is prime in here. And the converse is easy as well. But, okay with that? But actually, you can go a little bit farther there. So this looks exactly like a polynomial result, but there's something a little bit extra. And that is you don't always get power series bonuses, but you get a bonus. And this is I is max. If and only. And so when clear as an ideal of R, I is maximal if and only if this is an ideal of R power X. pointed out last time that this is even for a field, this is trivially not true polynomial, right? So for example, if R is a field, 0 is maximal ideal, but the ideal I comma X, which would translate to 0 comma X, which is the ideal generated by X, that is certainly a maximal ideal of polynomial ring, but that ain't it, right? There's many, many more. In fact, there's always infinitely many maximal ideals of polynomial ring. But you get a little something extra, you get a little power, right? And this is actually very powerful, and this is something that is strikingly different. And what makes it unusual is not only is it strikingly different, it's strikingly better in a certain sense, if you like ideals, than polynomials. Let me give you the following proposition that sort of brings us online. Let R be a commutative ring with 1, then there is a 1-to-1 correspondence. Then there is a 1-to-1 correspondence between ideals of maximal ideals. Of R and maximal ideals of R power X. And the correspondence is getting this way. Maximal ideal of R is M corresponds to maximal ideal of X. Right. So let me shake this one out, because this one's a big one. So that is, given any maximal ideal of R, M comma X is a maximal ideal of R power X. And the amazing thing is that's it. That's an exhaustive list, which is different from polynomials. So let's verify this. Suppose first M in R is maximal. So it's a maximal ideal. Then so let's use our previous theorem here. So what we've shown so far, given a maximal ideal M and R, that means R mod M is a field, but R mod M is isomorphic to that mess there from proposition 238. So that means that M comma X must be a maximal ideal of R power X. Okay, that's the easy part. Given a maximal ideal here, that M comma X gives you a maximal ideal up there. The interesting part of this is that's it. There aren't any other maximal ideals. So to finish this, it suffices to show any maximal ideal power x is a form of m comma for some maximal ideal Okay, so if we can show that every maximal ideal of this of our power x is in this form, then we've established our one-to-one correspondence because we have a function that goes both ways and it goes to the identity. M goes to this, which corresponds back to M and vice versa. Right? Okay, how do we do it? Any ideas? What's a good maybe first strategy? Yeah, I think that's not what good strategy. Let gamma or power x be a maximum. Notice, and this is actually what you prescribe, basically what there is on big enough concept here. By the way, gamma is an ideal of R power x. So when you intersect it down to R, it's an ideal. Of course, it contains at least 0, right? What can you say about this ideal? I'll call this M, but I don't want to be too suggestive. I don't know its maximal ideal yet, but I do know one thing about M. What's that now?
Can't be all of them.
Okay, yeah, it can't be everything. But there's. Yeah, that's not the prime thing. So gamma intersect R in fact has to be prime ideal. Do you all know this? That if you intersect a prime ideal with a lower domain, you always get a prime ideal? Well, maybe not. I gotta get some blank looks, and it's not just me. So why don't we prove that? Let me throw in a little lemma first for fun. Suppose you have little ring, big ring, right? And suppose Q in T is prime. Then T, which is Q intersect R, is a prime ideal. So when you intersect a prime down to a smaller ring, it's still intersect a prime down to a smaller ring, and that intersection is prime. That's actually a good thing to know. Let me point out that since Q is a prime ideal, I assume it to be proper, that its intersection down to R has to also be proper, right? Because I'm assuming the subrings contain the same identity. So if the identity of R is contained in P, then that means it's contained in Q, which is the identity of T, and it's not proper. Hope you did it so far. And it's clear to you all that this is an ideal, right? This is actually an ideal of R, right? Because certainly it's closed under addition. And if you multiply anything by P, then it's still in Q because it's an ideal upstairs. If you multiply anything in P by R, R is actually contained in T, so multiply by the Q part, it's still in there, and it's also still in R. So, yeah. Let's suppose P is a proper ideal. That's where we are so far. Now suppose A, B, our elements bar, right? Be careful about that. These are elements bar such that A, B is in P. Right? Now, P, of course, is contained in Q, and I know that Q is prime. Right? And of course, everything that happens in R can be construed as happening in T because T's the big ring. So if AB is in Q, this implies, without loss of generality, that A is in Q. Right? But now we have A is in Q and it's also in R, which is P. And there you go. So that's nice to know. So where are we right now? So we know that this intersection is a vector prime ideal. So now I'm gonna go one step further here. I claim M is max. Can anybody justify that for me? I hope it's not. Actually, you know what I wanted to do? I think what I want to do is something else. I wonder if I can still solve this direction. Yeah, I think actually, so the strategy here would be, okay, so M is maximal. Suppose if it's not maximal, it's contained in something bigger. So you can sort of join something else to this and make a slightly bigger ideal, call it Y, right? So you should be able to join that Y here and make something slightly bigger. But it could be that you're actually real, yeah. So I think I need to change this proof. Does anybody see what the potential problem is? So with my strategy, what I'm trying to do is I'm going to join Y to this M and make a bigger ideal. And I'm going to try to get a counter, or I'm going to try to run into a problem by, okay, I'm going to throw that into gamma and make something big. However, what is M? It's just all the constant terms. So I intersect, right? I don't think I want to intersect. Because the problem is when I throw that Y in there, there might be something in gamma that's not a constant term, but it's actually in a higher ideal because it's part of a bigger power system. Anybody know what maybe I should do instead? Okay, good. Let's go this way. So I'm glad I threw this lemon in because we're not going to have to use it, but it is good to know. We'll certainly use it later. So try to. Let's look down and do this. I'm trying to do M. That's what I'm going to say. M equals the set of F of 0, where F of X is in gamma. See, the first thing I did is I just swept out all the constant terms. Now, in a certain sense, I'm getting more because not only am I getting the power series in gamma that are just constants, I'm actually also sweeping out all the constant terms, right? So you might have something that's the constant term on a very large power series that ostensibly isn't floating around by itself to be a constant, right? It actually is, but we haven't proved that, right? So since I flubbed the first bit, let's actually sort of quickly verify that this is in fact an ideal. So let A, B, and M, and A equals F0, B equals G of 0 for some F of X, G of X, and gamma. Therefore, A plus B equals F plus G. Right. And so this M is closed under addition, right? Because constant terms add up. Also, if R is in R, then R times F of X is in gamma, therefore R F0, which is RA, is in gamma. Okay, so I'm feeling good about myself. This is an ideal. Right? And I claim now, right now, M be the maximal. Of R. Okay, so now I claim that, I mean, basically what I've done is I've taken my ideal gamma and I have read every single constant term out of every power series in there. We've shown that this is an ideal, now I claim it's maximal. Okay, why is it maximal? If not, then there exists a proper ideal M such that M strictly contained in N strictly contained in R. And I'm going to do a contradiction of it, right? I'm going to prove that this can't happen. You cannot stick another ideal strictly between M and R. So if there is, then let C be an N, but not M. Okay. And consider the ideal gamma Z. And I claim that that's a problem. Notice that, let me point out that gamma Z must properly contain gamma. So what I've done is I've just taken this constant, say, this rogue constant, and I've thrown it into gamma, and I've generated a bigger ideal. First of all, my first claim is it's honest to goodness bigger ideal. Bigger ideal. Can somebody tell me why?
Because Z's and Z's and M's.
Right. What's the constant term of this power series? It's Z itself, right? And so Z would actually have to be an M, which it's not. So this has to be a bigger ideal. Right? Therefore, gamma Z must be all of R power X. Right? So what does this mean? This means there exists gamma in gamma, and let's say let's not do that, let's say h of x and r power x such that gamma x plus h of x c is equal to 1. Correct. Now, plug in 0 and like that. Correct. And notice that this thing is in M and Z is in N, so this is an element of N. And they're contradictions in amplified. So there you go. This means so I've got that M is maximal, correct? Now, the last piece of the puzzle is I am now going to leverage this and show them. So the final claim is now show in comma x. Well, so let me point out that notice that gamma actually this is crap. So I want to show the gammas in comma x. So how about this container here? Why is this true? For this container, it suffices to show that x is a gamma. And how do we show that? How can we show that, how can we show that, in comma x is contained? How can we show that x? I mean, we already have shown that all of, or actually, yeah, it would suffice to show this, because once you have x's in there, then you certainly got everything in there as well. How can we show that x is in there? Okay, how are you gonna do that?
If X wasn't in there, would not be a maximal ideal, because we would still be able to add X, and given the nature of the coefficient, the constant terms,
Good,
we wouldn't get everything.
that's exactly right. Every constant term for an element in gamma is in M. Okay. And this means so I guess I should have done this first. This means certainly that gamma is contained in M comma x. Correct? because everything in gamma has constant term M. This is everything that has constant term M with complete freedom, right? It can be anything after. There may be some restrictions, right? And so we've got this automatically, and we finish it by the fact that gamma is assumed to be maximal. So we must have equality. And there you go, right? The key point was right here with this business with units that are different from power series, right? You can't have anything floating around that has a 1 as a constant term. You can do that in polynomials, you can't do it in power series, right? And so that's basically why these things are different. Yes.
Can you also show that the correspondence is 1-to-1?
Well, right, so, okay, so we'll go through this. So here's the way the correspondence is. Take a maximal ideal. So I'm gonna give you a function that goes in both directions. So we'll go from maximal ideals of our maximal ideals here. And then I'm gonna go the other way, M goes to MX, and you can do that as well, just by that same homomorphism we use in analysis flags, right? So let's show that the correspondence is 1-to-1. Start with an ideal here, M. That passes to M comma X under this function, which passes back to M, right? So it composes to the identity in this direction. And you really got to check it the other, but if you start here with maximal ideal, we proved it's in this form. When you go this way, it goes to M, and under this, it goes to M comma X. So this function composes to the identity in both directions. Okay, any questions on that? Let me give you a quick corollary that is absolutely irresistible to me. Corollary 2, 3. The unit 1. Default properties. Are or has the property if and only though our power X has one local to semi-local, 3 semi-quasi-local, 4 quasi. And I probably built some good life in order. But so what this really means is, and in fact, it's stronger than what I said. For example, if R is local, it means it's Noetherian and has a unique maximal ideal. This is true. If it's true for R, it's true for R power X. Because we already know that for a ring with identity, Noetherian is preserved in the power series ring, and there's a 1-to-1 correspondence between the maximal ideals. So this is preserved also in R power X. Semi-local just means finite for many maximal ideals, and Noetherian, again, the Noetherian is preserved. And in fact, it's stronger than semi-local because not only is if R is semi-local, so is R power X, but they also have exactly the same number of maximal ideals. And here's the not necessarily the theory and analog of this. And like I said, it is never the case, for a commuted ring one, the polynomial ring is, semi-quasi-local. If you have a polynomial ring over a ring with identity, it's always got infinitely many maximal items. And we'll probably look at that later. Okay, any questions? Okay, I think I have just time to make a definition and a quick example. We are starting now, that we've kind of got some, basic terminology background. We're going to start to delve into something that really appeals to me, called integrality. And this thing actually will come up in this chapter, and it'll come up. This notion comes up a lot. So standard notation. Inside T are rings. And if R is a domain, well, if R and T domains, then well, I didn't feel talent. If R is a domain, it's called a field. Okay. Definition 31. Let R be commutative and T be an R algebra. What this really means is that T is an R module and R can be construed, T itself is a ring. It's also an R module, R is a subring, contained in the center of T. Just think of this as a good kind of prototype. Just think of two integral domains and T's one that contains R. An element, but of course this language allows you to take up, say, maybe matrices or something like that. An element T and T is said to be integral over R if T is a root of a monic polynomial in Rx. What does monic mean? Well, it comes from mono meaning one, I guess. And it just means a polynomial whose leading coefficient is one. So let me write out my little monic friend there. So what it needs to be integral is just in some bigger ring perhaps, and it's the root of some polynomial coefficient one, and if every T and T is integral over R, we say the whole alpha is integral. So we'll do some examples and whatnot next time. You might think, here's a good, nice prototype. Think of the Gaussian integers over the integers. That is a good example of an integral. See if you can find a formula for what the monic polynomial would be in general. Okay, any questions? Questions out there? All right, well, y'all have a good one and we will catch you on the flip side.